Hey mathletes, here we are looking at logs and logarithmic functions. So a logarithm gives us the power to rewrite exponents. And the real value and benefit of this, okay, is the fact that we are able to solve expressions if we have an unknown in our exponent. Okay, so if we think about this example here, if we have 2 to the x is equal to 5. Well, I know 2 squared is equal to 4. And I know that 2 cubed is equal to 8. So I know that x is going to have to lie in between 2 and 3, but I really don't know exactly what value that's going to be. And then this, so far in our algebra careers, we don't really have a way to solve or know exactly what this value has to be. We know it's going to be a decimal between 2 and 3, but how do we get there? And that's what the power of a logarithm is going to do. Okay, so first thing, let's think about these cases when x is in the exponent here. Well, if we have nice numbers, okay, that are powers of, let's say, 2, we can say, well, 2 to the x is equal to, well, 4 is 2 squared. So by inspection, I can see that x and 2 are the same. So x is equal to 2. Okay. Um, Doing number 2 similarly, well, 1. Well, 1 can be written to 8 to the 0 power. And I have 8x. So therefore, by inspection, I can just say x is equal to 0. Okay. Next one, well, 2/3, 8 and 27, those work out really nice because 8 is 2 cubed and 27 is, fix that, 3 cubed, which is just 2/3 cubed. So if that's equal to 2/3 to the x, well then therefore by inspection I can again see x is equal to 3. Okay. On number 4 here we can see, well, fractional exponents, we should know that I can rewrite that fraction as 4 to the -1 because 4 was in the denominator, and then 4 to the x. And then I can see by inspection that x is equal to -1. Okay. Similarly, using fractional exponents on number 5, well, 4 and 2, how are they related? Well, I know that I can write 2 as the square root of 4, or 4 to the 1/2 power. And then I have 4 to the x on the left side. So by inspection, I can see that x is equal to 1/2. Okay. Similarly, kind of using the ideas of 4 and 5, I can write 1/2. Okay. Well, that's 2 is 4 to the 1/2 to be 2, but then it has to be negative to be a fraction. Well, this is equal, the left side is 40x. So then, therefore, by inspection, I see that x is equal to -1/2. So there are ones and expressions that we are able to solve for when x is in our numerator. But what happens when they're not so nice? Okay, we're going to use our logarithms, or what we refer to as logs in short. The log to the base b of a positive number y is defined as such. So notice, if we take the expression y equals b to the x, we could rewrite that as a logarithm. That is log base b. Notice the base is the same as the base of our exponent. So log base b of y, the y value is what your expression is equal to as an exponent. And your answer to a logarithm is always an exponent. Okay, so it's good to make sure you have this written down so that you can go back and forth, and that's our big goal today, is just to be going back and forth between an exponent equation and a logarithm equation and make sure we get those right. Okay, some things to note: the log of a negative number or 0 is undefined, so we're going to have some undefined that'll make more sense as we look at our graphs in our next lesson. Okay, but our base value has to be greater than 0, and it can't be 1. Okay, meaning when we have just with exponents, we didn't deal with exponents with b's being a negative value. Okay, for the same reason, our logarithms here, we're not going to allow that to be a negative as well. So the most common logarithm is a logarithm that uses base 10. It's one that's found in almost all calculators, and so we can write the log base 10 of y as just log of y. So if it's written as log of y, we assume there's an imaginary 10 here. Okay, this is analogous. Okay, so here we're going to practice writing in logarithmic form. Okay, so the first one is 729 equals 3 to the 6. So if I wrote this as a logarithm, it's log. Well, what's the base of my exponent? It's 3, so it's also the base of my logarithm. 729 is what it's equal to, and the answer, or the solution to the logarithm, is always our exponent. So I kind of talk myself through them as I'm working them. So 25 equals 5 squared. So if I rewrote this as a logarithm, it's log base 5 to the 25. So it's saying 5 to what power is 25? Well, the answer is 2. Okay. The last one down here, 10 to the 0 is 1. So I can say that this is log base 10. So I don't need to write it because it's a common log. To the first is equal to 0. Okay. So here's some other examples. Now here we want to write these going from a logarithm to an exponential form. So first one, I'm going to write the base of my logarithm is the base of my exponent. The answer to my logarithm, the answer is always my exponent, so this is equal to 16. Okay, this is log base 4, 1 equals 0, so it's 4 to the 0 is equal to 1. On C, it's log base 12 of 12 is equal to 1, or 12 to the first power is equal to 12. Okay, and here, log of base 1/4 to the fourth is negative 1. So I can say that 1/4 to the negative 1 power is equal to 4. So if you struggle with this, I'd suggest trying to use some color association in your notes to make sure you're seeing where the values correspond to. Okay, here in this example now we are just going to go the other way. We're going to take our exponential and write it as a logarithm. So we get log base 5 of 25 is 2. And we get log base 10 to 0.1 is equal to negative 1. C, we get log base 8 of 4 is equal to 2/3. Okay, log base 6 of 1 over 216 is equal to negative 3. So my self-check for really quickness is my bases. So 5 is my base, 8 is my base, 10 is my base, 6 is my base, And the answer to a logarithm is always an exponent. 2, solution, 2. Exponent, solution, 2/3. Exponent, negative 3, negative 3. Exponent, negative 1, solution, negative 1. Okay. So when we're evaluating logarithms, okay, sometimes it's useful to go back and rewrite them in exponential form. Write each side using some common base. For this example, we're going to use 2, but I'd always try to go down to the lowest common prime factor of the two numbers that you have. Okay, so for instance, if I want to evaluate log of 16 equals x, I'm going to write it as an exponent and say, okay, I know that this is saying 8 to what power is 16. Okay. Now we're going to write each side using the same base. For this one, it's base 2 because 8 and 16 are factors of 2. 8 is 2 cubed to the x. I'm just replacing that. And 16 is 2 to the 4th. Okay. Now that I have the same base, I can extrapolate and just use my exponent rules and say that 3x has to be equal to 4. Okay, so if I divide both sides by 3, I see x is equal to 4/3. Okay. So let's look at some other examples here. So log of 3 of 81 equals x. So this is 3 to the x equals 81. So obviously I'm not going to write them as powers of 2 here. But 81 can be written as a power of 3. 3 is already a prime number, so I can't reduce it in any other lower. 81 is 3 to the 4th. So now just dropping out the bases, now that they're the same, I can see that x is equal to 4. Okay. Similarly, I'm going to get 9 to the x equals 27. Right? So now I got to change both of them because 9 is not a lowest common prime. So I can write 9 as 3 squared. Now that's to the x. So just substitution. 27 is 3 cubed. So I use my power rule. I know that this is 3 to the 2x equals 3 cubed. I have the same bases. So now that I can say that 2x is equal to 3, divide by 2, and I get x is equal to 3/2. Okay, which makes sense. 3/2 is a 1.5. Okay, so if I think of 9 to the 1st, that's equal to 9. If I think of 9 squared, that's equal to 81. So 9 to what power is 27? It's got to be a number between 1 and 2. Well, it ends up being 1.5 because of the logarithmic scale. It's not necessarily 1 to 1. Just because 1.5 is in between 1 and 2 doesn't mean the number out is between 1 and 81. We can see it's 27. Okay. Next example here, we can see that we have 10 to the x is equal to 100. Okay. Well, 100 can be written as a power of 10, so I don't need to reduce 10. So 100 is just 10 squared. So now that I have them as the same basis, I can say that x is equal to 2. Our other example here, I get 64 to the x is equal to 1 over 32. So this one's a little bit more challenging to see, but if you think about all these 64 and 32 are powers of 2. Okay, so as I think about 64, okay, 64 is 2 to the 6th. That's the x. Okay. Well, 32 is 2 to the 5th. But because it's a fraction, it's going to be 2 to the -5th. And over here, I simplify and get 2 to the 6x. Well, now my bases are the same, so I can set those equal to each other, and I get 6x equals -5. Divide by 6, divide by 6, I get x is equal to -5 over 6. Okay. My next and final slide here is just looking at how do we calculate these with a calculator. In today's unit, we're just going to focus on our two basic evaluations with a common log. So this has an imaginary 10 here. And this is our natural base. So this is just log base e. We'll talk more about these in our next unit. But really what I want you to do is make sure you can identify and find these on your calculator. Okay. So if I go ahead and pull up my graphing calculator, okay, I'm going to see that my logarithms live right there in my calculator. So if I want to calculate, see if I can get my calculator to work here. So clear out my screen. I want to do log of 8. Okay. Ooh, kind of running out of screen here. Log of 8 is 0.903. And for the other answer of ln of 0.3, ln is just right there, and I do 0.3, and I hit enter. And so I get negative 1.204. Make sure you can identify those where they're at in your calculator. If you can't, bring it to office hours, and I can help find that for you. Please highlight any questions you have from notes and bring them to office hours if you have them.